next presenter is Chris Woodfield, who will be presenting Demystifying Clos fabrics, C-L-O-S. Chris is an automation architect and has traveled from Washington to join us today. Chris is also an active NANOG volunteer, previously serving on the program committee and currently co-chairing the hackathon committee. I'm very happy to welcome my friend Chris back to the stage.
Thank you. Thank you. There we go. And a clicker. That's great. The nice thing about the 4:30 slot is that there's a little bit less pressure, so I can pull things out of my back pocket if I want to, and fewer people are going to look at me sideways for it. So I'm here to talk about Clos fabrics. This is intended to be a fairly high-level design overview and a few different options for putting these together. Some of you in this room, there may not be a whole lot of new information, but hopefully everybody will learn a little something here. First off, who am I? If I had a beard, it would be gray. I've been in this business about 25 years and change. Spent most of my career in the backbone edge networking space, did a lot of BGP work, and that came in handy one day where I was basically put on loan to a data center team who was implementing a BGP as IGP routing model. And since then I've done a lot more data center stuff, so learning that. I'm not going to get everything right here. I always feel a little bit humbled coming on this stage. Feel free to ask questions or point out new information, new developments. Happy to listen. So I will start with just an overview of where we started here. Early data center designs, L2 designs primarily, the pros and cons of those, and then how we got from there to layer 3 design fabrics. Talk about the information you need to properly design and size your fabric and how to translate that into your outputs. Give some design options and then talk a little more about the details. So at the beginning, and by the beginning I'm thinking late 90s, one of the biggest vendors in the space had a very specific model of how to design a data center. Layer 2 was the coin of the realm. Spanning tree was a requirement for almost every data center design, which worked well for redundancy, but also gave you a bunch of drawbacks. You could not really get any significant load sharing. LACP was in the mix, so between individual devices you could share loads, but you couldn't go wide. You couldn't have multiple paths going through different devices. There were some proprietary extensions out there, but if you wanted a vendor neutral, vendor independent design, those were off the table as well. As people switched to layer 3, as people started deprecating spanning tree and moving to L3 fabrics, the hardware designs rarely changed. You generally didn't get to new hardware designs until you were ready to build a new core, build a new data center fabric. Eventually that happened, but it took a while. I have some fond memories of building L3 designs using L2 topologies. Now, this model, we call it core distribution access, and this was before underlays existed. So this is pre-VXLAN, definitely pre-Geneve. L2 requirements, you generally needed VLAN trunks with spanning tree, as I mentioned. Spanning tree is an active standby model. You could not share loads. You had your active link and then you had your blocking path. And if your active forwarding path went down, then traffic would switch over. But there was no load sharing, no ECMP. Your failover model was primarily through these horizontal handoffs that you see at each layer. Now, with 2 devices at each layer, that's a single cable. If for whatever reason you need more than 2, that gets a lot more complex. And spanning tree was a lot less reliable than a lot of people would like to admit. I've seen plenty of spanning tree meltdowns. I'm sure everyone here who's been in this business long enough has. And between then and now with L3 designs, you might remember you don't see as many catastrophic failures of a fabric anymore. And that's good news for everybody. Now when we talk about the Clos model, the Clos fabric, most of you know this, but if you don't, it is not an acronym. It is a name. It is named after not its original inventor, but its first implementer. The first patents around this design are from 1938. Edward Irwin was the patent holder on the original Clos design. Charles Clos, who it's named after, gets credit for the first production design at Bell Labs in 1952. Now, obviously, this was not designed for data. This was designed for phone call switching across multiple switches, so you could go horizontal instead of needing higher speed links. But it worked well for that model, and then there was a point where us internet engineers and network engineers figured out that it would also be a pretty viable model for data centers as well. So let's ask the question, what is a Clos fabric and what makes it unique from earlier designs? The biggest difference is that we have a very strong focus on horizontal scaling as opposed to vertical scaling. Not that you can't do vertical scaling. What you'll see in the later slides is that all of the speeds that you will see in the design examples are actually 100 gig, which is starting to go out of fashion. We're seeing a lot more 400 gig interconnects in these designs now. But a lot of people probably don't have the budget for 400 gigs, so I'm sticking with 100 gig for my designs and design examples at this point. Devices use load sharing, equal host multipath, to make use of all available paths between these layers. And if a layer fails, if a device fails, if a link fails, that traffic gets just shifted to the remaining links. So what happens then is that the available ports in a switch and your ECMP width, and one other thing, the number of switches, which is informed by limited by your ECMP width, are your primary scalability components, not necessarily your link speeds. And what this also gives you that you won't see any links between devices in a layer, which takes away your n minus 1 divided by 2 mesh complexity. Replaces it with other complexities, but in general, they're a bit more manageable. So why didn't we do this from day one? There's a few developments that had to happen before this became a viable data center model. The first one is improvements in ECMP features on switch hardware, router hardware. Those of you that remember the 2000s and the biggest, most popular data center switch of the day may also remember that it could only do 8-way ECMP. So that was your maximum width for spraying traffic across ports. What you might not remember is that its ECMP algorithm hashed your packet and generated a 3-bit hash. What does that mean? That means that if you have 2 ports, 4 ports, or 8 ports, you will get relatively level traffic between those ports. If you have 7 ports, or 5 ports, or 3 ports, you will absolutely not see even levels of traffic because each of those 8 buckets gets mapped to a single port. So you have 332 or 1111112, and that becomes your traffic levels. Another thing that happened is that as data centers became larger and more complex, a lot of operators started to run problems running IGPs, running OSPF or ISIS. Some more than others, depending on the design you picked. Multiple areas tended to get your IGP scale a lot larger than designs that stuck with area 0 for everything. But what we saw is that people started moving to BGP-based designs, where BGP became the IGP. And to be fair, IGP is still fine for fabrics of a certain size. I've even seen examples of very large fabrics that still use IGP. Very well-designed IGP, but still IGP. But BGP, until at the time when L2 data centers were popular, didn't support equal cost. Now, that has changed, and I don't recall if that actually made it into an RFC or that just became a de facto design that vendors operated, but that was the last piece in the puzzle, was being able to run BGP in a data center and still get ECMP multipath. So let's start with your, I need to build a new data center core, I need to build a Clos fabric. The first few questions that you'll want to ask yourself is, some of the design requirements is, are you planning on doing native routing between your hosts for your production traffic? Or are you planning on doing underlay overlay? Are you going to be using VXLAN or Geneva or any sort of other type of encapsulation for the traffic between your hosts, for the data? That's one thing that you want to keep in mind. What are your protocols? Are you running dual stack? Are you running IPv4 only? Are you running IPv6 only? This may inform how you aggregate your routes and make sure that you don't blow the TCAM if you're using lower end commodity hardware that don't have very large TCAMs. I would say that I hope you're not planning on only running v4, because if you don't need v6 now, you probably will need it eventually. So might as well build it, bake it into your design from day one. What are your other scaling constraints? What's the size of your cage or your room size? What is your power budget? What are your actual compute needs? What is the maximum number of servers that you're going to need to support? Are they Intel servers, AMD? Are they GPUs? Is this an AI training core? Now, we have seen, as our previous speaker mentioned, we have seen disaggregated cores. It is entirely possible to build a fabric that spans buildings. It gets a bit more expensive to run links. Given the number of links you typically see in these fabrics, you might have to do WDM in order to get them across fewer physical fibers, which also raises your cost, but it's absolutely a valid design. I've seen it implemented many times. What is the bandwidth per rack? And your server and your workload is going to inform this. Are your hosts 10, 2500 gig, or even 400 gig? How many hosts are you planning on having in your rack, depending on your rack size, your power requirements? You might have 40, you might have 20, you might have 10 with so much space in between them in order to get under your per rack power budget in the data center you're in. What are your oversubscription requirements? There was a talk yesterday that was talking about the different oversubscription tolerances of different types of AI training. There were some types of AI training that would take every bit of capacity on the wire, and as such, oversubscription had to be minimized. There are others that do quite well in an oversubscribed network. If you're an ISP, if these are web servers, you generally you have a diurnal traffic pattern, and you can probably handle quite a bit of oversubscription. And what is your fault tolerance? 50% is generally a rule of thumb, but if you have more, as your links go wider, as your ECMP spray goes wider, you can generally trust that you will have a lower percentage of your links in a failure mode at any given point in time. You might be a 70% or 75% capacity requirement, which means there isn't going to be a time where you can design around an assumption that only 25 of your links are going to be down at any given time, or 1/8. But something to consider, and use that to inform, that generally informs your oversubscription ratios. Because if you're going to lose half your links, you have to base your largest bandwidth based on that. If you're only going to lose 25%, that's a different number. So I've come up with 3 simple rules here. The first is to start your design off with the maximum scale that you think that, not that you'll need, not that fills your room, but that you're willing to put in a single failure domain. Remember, there is the capacity for a catastrophic failure of a fabric. So if filling a room with 1 will take your service completely down, if that fails, maybe you want to build 2 side by side, so an A and a B. That doesn't mean you have to build it all at the same time. You can build these out organically. You will want to reserve the ports to on your devices to accommodate the largest design, the full-scale design, but you don't have to physically put in devices. That doesn't make financial or operational sense because you're going to waste power, you're going to buy hardware too early, and all that. The last, and gets really important, and I am probably the 10th or 20th speaker to repeat this mantra, is that you will want a single source of truth for all of your provisioning data to build this. It could be Netbox or Nautobot or InfraHub. I hope it's not a spreadsheet, but I've seen that too. YAML, JSON files will fill this role. They're not the most optimal solution, but they will fill it. And automate the provisioning as best you can. If you've got templates where you can copy and paste the template in the box, that's your basic level of config automation, or you can push configs using Ansible. From there, you can go to ZTP provisioning if you've got the development hours to work on that. There's a bunch of solutions out there, and the efficiency you get is going to be directly related to the development resources and or vendor software management budget you're willing to put into it. So let's start with a few design examples. This may be the most complex design you will need depending on the size of your fabric. These are these spine switches, so an assumption I built into this is you're going to have 32 or 64 ports per switch. And in this design, you can generally assume that the number of leafs are going to be proportionate to the number of ports on your spine switches. So that's going to be generally your maximum scale, but that gets you 32 to 64 racks. And if that's your maximum scale, that might not be more than you need. You don't get a lot of bandwidth per rack in a 2-spine design, but this is where you can go out a bit more. So let's talk about the capacities that you get here. So 32 by 100 gig is and I'm not even talking about 400 gig. I'm assuming 100 gig, which is mid-level vendor gear now. At this level, you get 100 gig per rack, and if you say if you have servers with 1 gig ports, unlikely. That's fine. That's more bandwidth than you need. If you're putting 10 gigs, that gives you a 4-to-1 oversubscription ratio, which is fine for a decent number of jobs that are more data processing rather than bit blasting are going to handle those oversubscription ratios just fine. And the one thing to remember is that if you think you're going to need more bandwidth per rack than this, make sure that you reserve leaf ports for implementing additional spines, because that's how you scale your per leaf bandwidth in this design. As in this example, so we now have 4 spines in your fabric, and just by adding 2 switches and 8 more fibers, I think, 2 more fibers per rack, you've now doubled your cluster bit, your leaf-to-leaf bandwidth. So we now have 200 gigs at 50% redundancy. Again, with a 32 by 100 or a 64 by 100 gig in your spine and 1 rack unit fixed form factors. I'm not going to talk about chassis much in this at all. Most of these designs are going to assume pizza boxes, either one RU or 2 RU pizza boxes, and definitely mid-level hardware at this point. Even wider, here's an 8-way spine. So if we're putting 25 gig hosts here, we've got 1.66 oversubscription. Now notice, this is about the point where you can lower your expectations of simultaneous failures. So we're now looking at a maximum of 25% of your paths down versus 50%. And with that, and with 25 gigs per host, we're at 1 terabit per rack and a 1.66 oversubscription ratio. That's pretty good. Unless you need completely non-blocking, this will probably fit your operational needs. Now, you could also get 2 rack units with 100 gig ports per host. So 20 hosts, 100 gig per. You're now at a 3.33 3.333 oversubscription ratio. And that's not bad either, depending on your workload. Your workload is going to drive your design decisions, but probably more than anything else. In order to do this, you'll need a 2-rack unit leaf switch, just to be clear on that. Now, let's say you're bigger than that. You've expanded all the available ports on your basic leaf spine. So what we can do now is we can interconnect those fabrics. At this point, most people call them clusters at this point, together with what I call a super spine. You've also seen this. You also heard this referred to as a plane sometimes, but this provides bandwidth between clusters that are roughly equal to the leaf-to-leaf bandwidth within a cluster. We call it a 5-stage because every packet will go through a maximum of 5 devices: leaf, spine, super spine, spine, leaf. I missed the mention earlier, but the earlier design was what we called a 3-stage, again, leaf, spine, leaf. So expand this out some more. This example here is 4 clusters of 4 spines in each cluster, and then 8 super spines interconnecting them all together. I'm really doing this talk to show off my OmniGraffle skills, in case you were wondering. So with this design, we now have 200 gigabits per leaf at 50% capacity, but that could be 75% capacity if we're doing 8-way instead of 4-way in the cluster. You've got 1.6 TB per cluster at that 50% redundancy rate. And at this point, your cluster count is only limited by the superspine port capacity. If you have your 64 port switches, now note that each cluster requires 4 ports in this design. So 64 ports gets you 16 clusters. If at this point you start to put in chassis switches, you can go even bigger than that. How many line cards you got? Now, this is a design that few of you will see or implement, but if you are, you definitely know who you are, and probably the rest of us do as well. These are your hyperscalers. The main difference between this design and the previous design is that instead of having a one-to-every fabric from each cluster switch to from each spine to each super spine, you separate that out. So what we see here is that spine 1 in each cluster only connects to the super spine 1 plane. So we have 4 sets of super spines here. Your spine 2 connects to super spine plane 2, and so on and so on. This example has 4 super spines. You could go wider on the super spines, and if you want to expand the per intercluster capacity, the easiest scaling here is to expand the size of each of these planes. So you could go to 4 to 6 to 8, and that will proportionally increase your bandwidth between the clusters. What this gives you, there's a couple considerations here, is that inherently you wind up with less bandwidth per cluster than what you might have in your earlier designs. So what you're going to see is that in these designs, you'll typically see fewer leaves in each cluster. But at the same time, this dramatically expands the number of clusters that are supportable. So in the end, you wind up getting substantially more leaves. And again, expand the number of super spines, expand the number of planes, and you can get to pretty significant scales here on the big 3, big 4 hyperscaler levels. Now, another thing about this design is that because you're not connecting every spine to every super spine, your ECMP spray is narrower. Your ECMP is a quarter of the width that it was before. And in some cases that can help with reducing elephant flows. You can keep your capacity more uniform. The wider an ECPM width, the higher the higher the risk of uneven traffic flows between individual links. And reducing that will help a lot there. Now, don't even think of implementing this unless you are automating it. This is going to be a highly complex design, and you will want provisioning systems, you will want ZTP. There's just way too many elements in this to manage manually. So going into what I originally called the gory details section, we can talk about some protocol choices, and I'm going through this a little bit slower than I thought, so I will speed through this as reasonably as I can. eBGP, as I mentioned, tends to be the most widely used. It's a routing protocol on a fabric, but it's also the most configuration intensive. So again, automate your pure configs. There's some things you could turn on. Passive BGP might help with here, but just keep that in mind. OSPF is perfectly fine for up to a certain size, or if you're really good at your OSP design, larger sizes. Overlays generally are still going to need BGP. So if you're doing OSPF as your IGP, you may need BGP between your leaves in order to support VXLAN or Geneve. Pay careful attention to your route LSA scale if you're going through this. A little bit about BGP models that I want to talk about. You want to assign unique ASNs to your leaves so that each rack has a unique ASN. However, your clusters, your individual clusters and your superspines should all be numbered out of the same ASN. Why? This gives you free loop prevention. You won't have routes bouncing between spine A, leaf, spine B, or spine A, superspine, spine B. That will, the loop prevention inherent in BGP will give you that benefit. Be careful where you aggregate. There are some corner cases where you might wind up following an aggregate route to a device that might not have a specific leaf route if there's a link failure. That's a major consideration in the multiplane design, but just keep that in mind and make sure that you don't aggregate in a way that risks losing the more specific routes. Now, BGP does not have the best keep alive timers in the world. 30, 90 is generally the default, and increasing that tends to drive up your control plane CPU. That's generally handled on the control plane. So instead of lowering that, consider a BFD. But something else to keep in mind is that these are all direct links. So the loss of a link will tear down a BGP session in maybe 50 milliseconds, and that might be the loss detection you need. And that's generally where you see BFD. I mean, I see BFD tuned to 25 to 100 milliseconds most of the time. So losing link might be good enough. Now about your addressing. Please run v6. There's no reason not to, and unless you're never going to use v6, which I think is unlikely, at the minimum dual stack. You might be able to do a v6 only underlay if all of your production traffic is overlay, even if it's v4 overlay. The underlay protocol doesn't matter. So if you can do v6 as your underlay, do so. If you're doing dual stack, you could also use RFC 5549, which allows you to advertise v4 NORIs over a v6 peer. So consider that as well, and that may eliminate the need for v4 link addressing. Now, the one place you can aggregate is your aggregate device links, your loopback and your interfaces. A reason to do this, especially for running v6, is that a /128 generally does not go into host TCAM. It still goes into LRU TCAM for most chip designs. So they're going to be a bit more expensive to store than you might think. So if you can, aggregate your link nets and your loopbacks. GSHUT's another thing to think about. If your BGP policy doesn't support, if your devices don't support it natively, some vendors, NASs support this natively, it can be implemented in policy. And what this effectively does is you match a community, and when you see that community, you set the local pref on that route to 0. So this is really helpful. It's very similar to OSPF overload. So what makes this, gives you a simple way of pushing traffic away from a device that is that is experiencing a failure, but it's still online, so you can do troubleshooting. Now, the biggest thing you'll run into in these kinds of designs is individual link troubleshooting. As you see here, with this design, with this Clos fabric design, there are 128 possible paths between leaf 1.1 and leaf 4.1. That's a lot if you've got one that's lossy. If there's a failure, that's easy. Traffic goes around it. But if one of these links is, say, dropping 10% of its packets, and you don't have a reasonable way to isolate that failure, you're going to have a really bad time. The best recommendation I can think of, and there might be newer ones, is an application called PigMesh. It's open source. You can find it on GitHub. And what that does is that gives you a way of testing every available path between 2 points. It varies the source UDP ports so that it works the hash, so that it gives you every possible hash bucket, and then that helps you identify an individual path that fails, and then from there you can identify individual ports, and then find your lossy link and take it out of service and do your repair. And 45 seconds for questions? No. Negative 45 seconds for questions at this point. I hope this was a helpful talk. Thank you very much. And do we have time for questions or not?
You may have one question.
I may have one question. And I see Jake in the back for my one question. You are on, sir.
Hi, Jake Kuhn, unaffiliated as well. First of all, great talk. I may borrow it at some point. Secondly, and I realize this may not be something that you can include in this talk, but maybe another talk that addresses why you would pick one design over another for different types of applications and workloads, and what the implications are of each design on distributing workloads and things from a cloud SDN standpoint, for instance.
Okay. I probably need 45 minutes if I did that, but that's excellent feedback.
Right.
And their AI does not show up in any of these slides, so you can obviously tell that I'm behind the times quite a bit. So,
and my final comment is: be careful with BFD especially on the top of rack switches, which tend to be built on more commodity hardware.
Yes.
And so BFD can be pretty intensive, especially if it's not centralized and not running on the ASIC. And so with a scale of BGP sessions, you can start getting to BFD flapping conditions.
Yeah, I think a rule of thumb here is check your BFD implementation. If it's running on your switch ASIC, that's probably fine. If it's running on the control plane, stay the hell away from it. That sound reasonable? Okay,
All right. Thank you very much, Chris. Next up is going to be Chad Lamb. Yes, let's applaud Chris.